The third device we're going to build is called a multiplexer. Now this is a fancy word for a selection box. Basically what happens is you have a number of inputs coming into the box. We're going to say we have 4 inputs in this example, D3, D2, D1, D0, and multiplexers look similar to decoders in terms of the shape of the box that we use, but it's a little different. What we're going to use here is we're going to say we have 2 bits. We're going to call them selection lines, S1 and S0, and they're going to behave somewhat like the address lines. But instead of activating one object, we're going to select one object. So we're going to say these 4 inputs are coming in. We're going to use these 2 bits to select which of them we want, and then the result is going to go out on Q. Okay? So we can draw a truth table for this. There are, in fact, 6 inputs, which is going to be very messy. We can't do a 6-input Carnot map, for example. So we may have to think a little bit more carefully when it comes time to designing the circuit for this device. And you'll find that as well. As you get into bigger and more complicated devices, Carnot maps may or may not give you the answer you're looking for. So let's draw out a truth table for this, and it's going to look a little different than our regular truth tables. We're going to have 2 inputs, S1 and S0, and as usual, the S1 and S0 have these 4 possibilities. And then we're going to have an output Q. Now we're missing a whole bunch of inputs, right? D0 could be 1 and 0, D1 could be 1 and 0, D2, but really we don't care what the value of those data inputs is. We just want to route that data input through to Q. So if S1 and S0 are both 0, our output Q is going to be equal to whatever D0 is. And if it's 0, 1, it's going to be whatever D1 is. If it's 1, 0, it's going to be whatever D2 is. And if it's 1, 1, it's going to be whatever D3 is. So this is going to be the truth table for this multiplexer. We abbreviate it as MUX, because that's what we do. So how are we going to do this? Well, this sort of feels a little bit like what we were talking about before, where we have a pair of lines that's going to activate one option, right? We're going to select one line in a memory, or we're going to select one register out of a bunch. We're selecting one input out of a set of data. So maybe we can use the decoder, which was the idea that we had before. We can take our decoder, this is our decoder, and we can activate one output for the input combination. And maybe based on that output, then we can say, our input line is here. Maybe we can combine them somehow so that if this is active, our output goes along, and if it's not active, then it doesn't. What we really need is a device that will allow a line to be permitted to pass or not to pass. And surprisingly, we have one of those things. What we have is, if we have a data line coming in like this, and we want to have a selection line here, that selection line is going to permit or not permit the data line to come through. Now, can you guess what that should be? In fact, it's very easy. An AND gate. This serves as a control flow gate. If we have A, then we have 2 options. If S equals 0, the output is 0, right? I'll call this Q. If S equals 0, our output is 0. There is no flow of data from A through to Q. But if S equals 1, then our output is A. Because if S is 1, it doesn't matter what A is, the result will be A. If A is 1, 1 and 1 make 1. If A is 0, that forces it to be 0. So we can treat an AND gate like a selector line. If one input is our controller, and then the other input says whether the result is 0 or the result is the same as the data that's coming through. Now, how can we make this useful when it comes time to building out our multiplexer? Well, we can have a number of select lines, and based on whether those select lines are 0 and 1, we can activate, allow to pass through, or not pass through the data lines. Similarly, we can take our decoder, we can put an AND gate at the end of each of these and have our data lines routing through here. In the end, what we'll see is it's the same circuit, which is kind of interesting. So let's build out a 2-bit decoder. We're going to actually put 2 of these AND gates down. And the select line is going to be inverted for this one. Let's see if I can put that there. And not inverted for this one. Now let's look at what this actually is. We'll call this D1 and we'll call this D0. For this output here, if S is 1, this output is equal to, we'll call this, in our decoder, we call those Ds. This is sort of an intermediate one. If S is 1, this is D1. If S is 0, this is 0. Same with this one. But it's backwards. If S is 0, this is equal to D0. If S is 1, this is equal to 0. All right, this seems kind of messy. We should have some sort of a representation for this. And of course we do, right? We can equally say this is equal to D1S and this is equal to D0S prime. And then all we have to do is OR these two things together and we'll get an output Q that corresponds to whichever of these is selected by this. If S is 1, then Q is going to be D1. If S is 0, then Q is going to be D0. So this is actually a 2-to-1 multiplexer because we're having 2 inputs coming in and we're selecting one of them. A multiplexer is always 2-1, by the way. This one up here is a 4-to-1. So let's build the circuit for this 4-to-1 multiplexer. And we're going to use this truth table and we're going to build out a circuit that says that our output should be equal to the OR of S1 prime S0 prime D, S1 prime S0 D1, S1 S0 D2, S1 S0 D3. If we AND each of these together and then we OR the result, we're going to get our multiplexer. So I'm going to build that out here, and then we're going to look at how that compares to our decoder. So the multiplexer is going to look like this. We're going to have D3, D2, D1, and D0, and we're going to have our select lines S1 and S0, and we're going to have an AND gate for each of these D inputs. These AND gates are going to be activated by these select lines. We want this AND gate to be activated when this is 3. 3 is 1, 1, so here's 1, and here's 1. When S1 is 1 and S0 is 1, this AND gate will be active. And we don't want any of these to be active, but that'll take care of itself because each of these is being selected by a minterm. So D2 is going to be active when S1 is active and S0 is not. D1 will be active when it's S1 prime, S0, and D0 will be active if it's S1 prime, S0 prime. Those are the 4 minterms, each ANDed with an input combination. And again, if we look back at our decoder, this looks awfully familiar. There's an AND gate for each possible minterm. In this case, they're all activated by an enable. Here, they're each activated by the input line that's coming in. Now, the difference with a multiplexer and a decoder is we want one output that corresponds to the data input on that minterm. And so we are ANDing all of these together. Each one will be active only in one possible situation, and so we're only going to get one of these data streams routed through to Q. That's the fundamental circuit for a multiplexer, and then we'll talk about a demultiplexer, and we'll see how those 4, multiplexer, demultiplexer, decoder, encoder, how they all sort of relate to each other.